Good morning, guys. This is Miss Perry. We are going to be talking about free fall and gravity today. And the first thing I want to talk about is universal gravitation, and this is gravity in the universe. So every mass in the universe reaches out and pulls on every other mass. That's why we have orbits. That's how the Earth orbits around the sun and the moon orbits around the Earth. Now, Newton knew that forces cause motion to change. You had to have a force to make an object accelerate, either speed up, slow down, or change directions. There had to be some kind of force that caused that. And he was puzzled why the moon curved around as it orbits around the Earth. So there must be something to change its direction. And the apple, when it falls to the Earth, he understood that, but the moon is pulled down by the Earth, but it doesn't fall. So that was a little bit puzzling to him. Okay, so it's like a projectile that never lands. If you throw a ball, the ball is going to eventually hit the ground, but the moon didn't do that. It just keeps going around the Earth. And if it didn't fall to Earth, then it should move off in a straight line. Like if you threw a ball and it just went straight instead of being pulled down to the Earth with gravity. And the force of gravity is affected by the distance between the objects. So the Earth goes around the sun, but it's not pulled into the sun. The moon goes around the Earth, but it's not pulled into it. But if the moon went further out, went further away from the Earth, at some point it's not going to be pulled in by gravity because it's going further away. So that's what this means. The force of gravity is affected by the distance between the objects. Okay, so let's look at gravity specifically. Gravity is a type of acceleration, and it's toward the center of the Earth. So this is where this is shown by little g, and little g stands for the acceleration of gravity, which is 9.8 meters per second, or 9.8 meters per second squared. So this is a type of acceleration. Now, there's a couple of things I want to show you. You have heard mass and you have heard weight. Well, there's a difference between the two. Mass is how much matter or how much stuff is in an object. Weight is how gravity is affecting that object. So weight is mass times gravity. Okay, so this is our formula to find out what weight is. So if you're given mass, then you're going to be able to calculate weight. And this little g is gravity. So that's the 9.8 meters per second squared. All right, so with free fall, this is kind of like if you're thinking like a skydiver, that they're in free fall without a parachute. So when an object is thrown up, like if you're throwing a ball up in the air, it's going to eventually start slowing down because gravity is pulling it. So every second it falls, the speed is going to increase by 9.8 meters per second. So objects accelerate as they fall. So think about that for a minute. You're throwing a ball up in the air, and eventually that ball is going to slow down, and then it's going to stop at the top for a quick second, and then start coming back down. Well, as the object continues to fall, it's going to speed up. And that's what it means by the acceleration of gravity. It's speeding up by 9.8 meters per second every second it falls. Okay, so Galileo looked at free fall also. And you've probably heard about the experiment where he threw things off of the Leaning Tower of Pisa. So if you're up on a roof, let's say, and you have a tennis ball and a bowling ball. Okay, let's don't do that because you might hurt somebody. But let's say we have a tennis ball and a bowling ball. If you drop them both at the same time, they're going to hit the ground at the same time. Okay, because we're not looking at any kind of air resistance. We'll talk about that later. But acceleration of gravity is you have the same object, or it doesn't matter what the mass is, the acceleration of gravity is going to pull it down at the same rate. Okay, so both of them would hit at the same time. And that brings us to something called terminal velocity, that you do have air resistance pushing up on objects. But things like bowling balls and tennis balls, it's really not that much just because of their masses and the way they're shaped. So air resistance doesn't really affect them. But think about a parachute. If a skydiver is falling through the air and he's in free fall until he pulls his parachute, then you've got air resistance going into the mix, and the air resistance is going to slow him down. Okay, so, but let's go back to terminal velocity. If you have a skydiver falling through the air and he doesn't pull a parachute, he doesn't just infinitely increase his velocity. There will be a point where his velocity will not increase. Now let's look at another example. If someone goes up, I think there's a story about this, that if someone goes up on top of the Empire State Building and drops a penny, okay, the thought was that the penny would make a dent in the ground when it hit the ground. Or that if somebody was down there and it hit them in the head, it would kill them. Okay, so let's think about that for a minute. If you have a penny that is falling from the Empire State Building, it's going to increase by 9.8 meters per second. The velocity will increase every second. But at some point, it's going to reach terminal velocity. It's not just going to infinitely increase velocity so that it goes through the ground. That's just not going to happen. But it's going to increase the velocity until it reaches the terminal velocity, until air resistance is stopping it from accelerating. Okay, it's going to slow down the acceleration. So it's going to reach a terminal velocity where it doesn't speed up anymore. And that's why it doesn't go through the earth. It won't kill somebody if it hits them. But let's don't do that one either. Okay, so now we're going to do calculations. You know how to do velocity with acceleration. Okay, velocity is acceleration divided by time. Okay, so that's one of our velocity formulas. So when an object is in free fall, you're going to use your acceleration is going to be gravity. Okay, so if an object is not in free fall, you're using the acceleration, normal acceleration, like if a velocity of a car driving down the road. But when an object's in free fall, you're using the acceleration of gravity. So it's still acceleration, it's just a special type of acceleration. So in any of these calculations where you have A for acceleration, you can substitute a G as long as it applies, as long as you have something falling in free fall. Now, the total time in the air has to be cut in half when doing these calculations because you're calculating something going up and something coming down. Okay, so it's kind of funny. You have to cut that time in half. All right, so let's look at an example. This is kind of like we were talking about with the penny on top of the Empire State Building. If you throw a ball from the top of a mountain, cliff, building, whatever you're standing on, then at the time you're letting it go, you're at 0 seconds and you have 0 meters per second. Okay, so that's your starting point. After 1 second, and 9.8 is rounded in this example, and you'll see that sometimes we're going to use 9.8 in calculations, but in some examples you'll see it rounded to 10 just to make it easier to calculate. Okay, so after 1 second, the velocity is 10 meters per second. Okay, at 2 seconds, it's 20 meters per second. So it has gone 2 seconds and it's 9.8 meters per second squared. That's your acceleration. So for every second, you're increasing by 9.8, or in this case, 10. So you increase by 10 for every second that it's falling. So after 3 seconds, it's speeded up to 30 meters per second. That's why these are different distances away from each other, because it's speeding up. After 4 seconds, the object is going 40 meters per second. Okay, and after 5 seconds, it's going 50 meters per second. Okay, so that's what we mean by free fall. It's going to speed up with the acceleration due to gravity, which is 9.8 meters per second, or like I said, sometimes it's rounded to 10. Okay, and this shows just a little bit differently. This is with the 9.8 in case you want to be a stickler like I am and use the 9.8 instead. So at 1 second, it's your acceleration due to gravity is 9.8 meters per second. Okay, that's after 1 second. After 2, it's 19.6 meters per second. After 3 seconds, it's 29.4 meters per second. And you can see so on and so on. It's going to speed up every second by 9.8 meters per second. Okay? So that's your acceleration of gravity. Now, calculations. We're going to look at how fast would a rock be moving after falling for 4.5 seconds, or after 8 seconds, or after 15 seconds. All right, so you've got velocity is equal to acceleration times time, but because it's free fall, we're going to use the acceleration of gravity, so we're going to use little g. All right, so you're going to plug in 9.8, and your times are going to be different. So with 4.5 seconds, it's going to be 44.1 meters per second. Okay, and they're negative because of the direction they're falling. So don't let that trip you up. Don't worry about it being negative. It's just showing the direction. Okay, so after 8 seconds, it's 78.4 meters per second. And then after 15 seconds, it's 147 meters per second. So the rock is going to be speeding up the longer it's in the air. All right, so we're also going to be talking about distance. And the distance that we're using, that we've been using, is acceleration times time, 1/2 acceleration times time squared. But since g is a type of acceleration, you can substitute it in the equation as long as you're talking about free fall. Okay, as long as you're talking about free fall, you can use g. All right, so let's look at this example. A base jumper falls for 5 seconds before opening up his parachute. And so what is the speed just before he pulls the ripcord? So if he falls for 5 seconds, that's our time. And g is going to be, or little g is going to be our 9.8. That's going to be our acceleration due to gravity. So you're going to calculate that, and you're going to get 49 meters per second. Okay, so now we know how fast he was going, but let's figure out how far he fell. So you're going to, again, substitute g for a, because it's free fall we're talking about. So then it's 1/2 times 9.8 times your time squared. And you're going to get 123 meters. So that's how far he fell in those 5 seconds, 123 meters. Okay, so let's look at practice problems. We're going to look at a coyote dropped a rock to hit the road runner on the road below. If you've never seen this cartoon, please go back and look because they're so cute. Okay, so the coyote dropped a rock to hit the road runner on the road below. If the rock falls for 2.5 seconds, how fast is it going when it hits the road? Of course, it's going to miss the road runner because it always does. Okay, so you have your time is 2.5 seconds. Your gravity, or little g, is 9.8 meters per second squared. And again, meters per second squared is just the unit. Do not square any of the numbers. Okay, it's just the unit. All right, so we're going to be using v equals gt. So that's your velocity. So we're just going to plug things in. You've got 9.8 is your acceleration due to gravity. 2.5 is your time. So you just multiply those together and get 24.5 meters per second. Now, if the rock hits the road below after 2.5 seconds, how high was the cliff? Okay, so we know how fast. Now we want to know how high. So we're going to use, well, we have our time is 2.5 seconds. Little g, acceleration due to gravity, is 9.8 meters per second squared. So we're going to use our distance calculation with little g instead of a because it's free fall. Okay. So we're going to use our formula right here. So you've got 0.5 is the same as 1/2. 9.8 is little g, and then 2.5 seconds is your time squared. Okay, so you're going to get 30.6 meters. Okay, so that's how high the cliff was when he threw the rock. Okay, so your assignment is the application problems on page 232. You're going to use this velocity equation. Little g is 9.8 meters per second squared, and this is your distance formula. Okay, so these are the formulas you should be using for this. I know sometimes it gets a little difficult figuring out what formula to use, so I'm going to go ahead and tell you these are the ones you're going to use. Okay, so text me on Remind or email me if you're having problems with it or if you have questions. Otherwise, I will talk to you later. Bye.